So we'll be discussing principal stresses a little bit more. We've done that in the previous lecture, but we're going to revisit some of that today. And what we learned in the previous lecture is that if I were to extract a cube or an excise a cube from a point from the structure, and I were to represent as a cube with 6 faces, then you're going to have 3 components of stress acting on each face. And these 3 components of stress comprise of the normal stress and tangential stresses. The first subscript, this is supposed to be sigma xx. So this stress component that's normal, the first subscript there corresponds to the face we're discussing whose normal is along the x direction. The second subscript, which is not shown here, sigma xx, that x there, which is the second subscript, corresponds to the direction that stress is acting. And you can see it's going to the right. So therefore, sigma xx. In this case, tau xy, this x is in the x phase, but it's pointed in the y direction. And then similarly, we have this tangential stress, that's sigma xc, x phase, z direction. And then you have stress components here, in the opposite phase. Sigma xx is pointed in the opposite direction, positive, and these shear stresses are pointed the opposite of what you see here, and that has to be true for equilibrium to be, for the system to be in equilibrium. So one of the questions we asked was, if I were to find an oblique plane, some sort of plane here, is there a plane at which the traction force acting on that oblique face is perpendicular to that surface? So there's no shear stresses in that plane. And so what we're really asking was, in which orientation this oblique surface needs to be, such that the traction acting on the surface is purely normal to that surface. That's the question we're asking. So there's no shear stresses acting on this surface. And if that is the case, if the normal n to this surface is n, if the normal n is n, this n here, then it has to be that if the traction is along the n, that it just be a scalar times n. It has to be, if it's aligned. If t is aligned with n, it better just be a scalar times n. It has to be. And we also derived Cauchy's relationship, where he stated that the stress components at a particular point times the normal that what? So we've demonstrated that the stress field, or the stress second order stress tensor times the normal to the oblique surface is equal to this traction here. And that traction has to be aligned with a normal too, because we said that it was aligned. And we're trying to figure out what oblique surface makes that happen. So you have a lambda there. And so if I were to bring this right-hand side to the left-hand side, I can factor the vector of the normal vector, and I get lambda subtracted from the diagonals. And what I get now is an eigenvalue problem, because the normal cannot be 0. So the determinant of this matrix here has to be equal to 0. And so what we discovered then is that you get this system of equations. The determinant of that gives you a characteristic cubic equation for which you can solve for 3 roots for lambda. And each of those roots for lambda corresponds to the principal stress of sigma 1, sigma 2, sigma 3. And for each principal stress, you have a corresponding oblique plane where there's only normal stresses acting on that surface. So it looks like this here. It looks like that. You have 3 normal stresses, only no shear, and this is the corresponding direction. N3, and sigma 3 is the magnitude of that, for example. And so I give an example of providing a stress field. I showed you that you subtract lambda from here, from the diagonals, then you do the determinant, and you get this characteristic equation. And then we find the three roots that can then be substituted back. One of them can be substituted back to get these three equations. And then once you have these three equations, you can then solve two of them in combination to the fact that n1 squared plus n2 squared plus n3 squared is 1, because n is a unit vector. So that will give you one of the directions that corresponds to sigma equals 4, for example. So that's what we've done. I also showed you the potential of exploiting MATLAB capability to solve the eigenvalue problem. If you just run this code here, it will produce the state, it will give you the state of stress that you're looking for, the corresponding principal stress, and the vector, the eigenvector, or the normal to the oblique surface that corresponds to that stress, where there's no shear stresses on that plane, only normal. So I want to give another example here. And the question is, given the state of stress, and this is the state of stress I'm giving you, find the principal stresses and directions. And what does that mean? What does that mean? What does that mean? If I tell you that I'm giving you the stress state here, and I ask you find the principal stresses and directions, what does that actually mean? What we mean with that is there are three mutually orthogonal planes, N1, N2, and N3, cutting through the infinitesimal cube, where the stress is normal to that plane, and there's no shear stresses in any of these planes. That's what we're talking about. So another way to view that is that I can cut a cube out, and if I were to cut a cube out, it's going to have the shear stresses and normal stresses. But I can also cut a cube out from the body of material, excise it out, a very small cube, and that cube can be oriented in some arbitrary angles. There is a particular orientation of that cube when I excise it out where the stresses are only acting normal to each of the faces, and there's no shear stress. Max principal stresses are very useful, and we will see later when we cover failure theories to explain why that is useful, particularly in brittle materials. It's a good way of predicting failure for brittle materials. In this case, I gave you the stress state, and the stress state is this one, for example, where sigma xx is 2, and then the sigma yy is 3, and it's not showing up, but that's sigma yy. And then -3 is sigma zz, and the off-diagonal terms are the remaining shear stresses. So all we have to do then is subtract minus lambda from the diagonals in this manner, 2 minus lambda, 3 minus lambda, -3, and there's a minus lambda missing here. I really apologize for that. So to make sure that we're in the same page, we'll correct that here and state that this is supposed to be -3 minus lambda. Apologies for that. And then you can find the determinant, and when you do that, you get 3 roots here, and because you can solve this cubic equation, and you can see here that one of the roots is lambda equals 2, and here this is lambda equals plus minus 5. So very simple to solve. Then you'll choose one root. Let's just choose one root for now. I will choose this one. And if I choose that root, I'll substitute 5, for example. I'll plug in 5 here again. So then I have 2 minus 5, 3 minus 5, and -3 minus lambda. So this is also supposed to be -3 minus lambda. And when you multiply it by this vector, you get these 3 equations that you see written here. you can see that I have 2 there. That's this 2. Lambda is minus 5. 5, sorry. So that's 2 minus 5, which is minus 3 and 1. So that's your first equation equals 0. The second equation is tau xy is 0, right? So that's 0. Sigma yy was 3. 3 minus 5 is minus 2. Minus 2 and 2. And tau yz was 4, if you recall, right here, 4. So then I have 4 times n3. That's my second equation. And I plug in finally 5 on the bottom equation. So I have tau xz is 0, as you can see here. Tau yz is 4, so that's that. And then tau and sigma zz is minus 3. Minus 3. And the lambda there is 5. So minus 3 minus 5 is minus 8. That's my second equation. Now all I have to do, I have n2 as a function of n3. I know n1 is 0, so you can set that 0. I know n2 in terms of n3. Both of these equations gives the same answer. So n2 is 2 or n2 is 2 here. It doesn't matter. But you know that n2 can be written in terms of n3. Once you do that, since this is 0, you can then solve for n3 here, because n2 is basically twice of n3. And so you can factor n3 out. And when you do that, you get 1 over square root of 5. And you can solve for n2, which is twice of n3. We can see that from any of these two equations. And so finally, because n1 squared plus n2 squared plus n3 squared has to be 1, you can see here that there's no n1, right? No n1. So that's why there's no e1 hat. But there is a 2 over square root of 5 and times e2 hat plus, and then 1 over square root of 5 e3 hat. And somebody had asked, can be either sign. Yeah, it could be plus minus 5, doesn't matter. We're defining the normal to the oblique angle, and that's what matters. So that's how we did, we do that problem. And you then repeat the process for the remaining 2 roots, and the 3 vectors should be mutually orthogonal to each other, meaning if I take each, if I take the dot product of n1 and n2, you should get a value of 1. And then if you do n2 hat dot n1, sorry, it should be 0. And then n1 hat dot n3 hat should be 0. This is orthogonal to each other. And so that's you can check it later when you're done. So you repeat it with the remaining 2 roots. I did it for lambda 1 equals 5. You can repeat it with lambda 2 equals 2 next, and then lambda 3 equals minus 5. And that's going to help you with completing the work. So hopefully this full example going step by step is helpful to you. In this next example is looking at Cauchy's relationship, just as an example, so you guys can see how that's applied. So if I have stress components as shown here, so these are the stress components I'm looking at, and I want to find a stress vector on a plane normal, and the normal is this one to the oblique surface. So I use Cauchy's relationship again. N is defined by this plane, but it needs to be a unit vector. So you have 1, 2, 1, 1 squared plus 2 squared plus 1 squared 6. So square root of 6 has to be in the denominator so that this becomes a unit vector. The stress has to be written carefully. So sigma xx is 80, that goes here. Sigma yy is 60, goes here. Sigma zz is 20, goes here. Those are the normal stresses to each of the faces, while the remaining components go in the diagonal terms. 20, 40, and then 10. And I'll show later that the stress is symmetric. We'll see that later. So the traction vector then, acting on that plane, is going to be sigma dot n. So I have the matrix here, the stress, times n, and I get this as a traction vector. It turns out that this traction vector is not normal to that surface, meaning that there are shear stresses also acting on that surface. If I want to find a traction component that's normal to that surface, I'll simply take this traction vector and dot it with n. And that will give me the component of stress that is normal to the oblique surface. So that's how that problem is completed. And hopefully that is clear to you.